In this video, we are going to talk about the Hardy-Weinberg equilibrium, and I will demonstrate how selection violates this principle through an example about monsters. A population of monsters has two types of coat color. Blue, which is big B, is dominant to green, which is little b. And there's a heterozygous dominant monster as well, which is big B. In this population, there are 200 big B monsters, 900 big B monsters, and 550 little b monsters. The Hardy-Weinberg equilibrium is a principle that states that genetic variation in a population will remain constant from one generation to the next. For this to occur, we need a large population size, random mating, no mutations, no selection, no migration to occur. This equation is p squared plus 2pq plus q squared, and this needs to be equal to 1 for there to be a Hardy-Weinberg population. The homozygous dominant, which is big B, represents the p squared. The heterozygous monsters, big B, represents the 2pq, and the q squared is little b. Is our population consistent with the Hardy-Weinberg? To find out, we need to find the frequencies of our big B and little b alleles. Our equation for the frequencies is f big B equals 2 times the big B plus big B divided by 2 times the total. And our equation for the little b is either the same, substituting the little b in for the first part, or you can just take 1 minus the frequency of the big B allele. Our frequency for the big B allele is 0.3940, and our little b frequency is 0.6061. If we add those numbers together, we should get 1. Next, we need to find the expected genotype frequencies. This is when we use our equation of p squared plus 2pq plus q squared. Once we find these numbers, we total it up, and it should equal 1. If we get an answer of 1, that means their population is consistent with the Hardy-Weinberg equilibrium. From this table, we can see our initial frequency, our fitness, the unadjusted survivors, and the frequency after our selection. We can find these values by multiplying the initial frequency by the fitness to find the unadjusted survivors, and we can use our average fitness equation to then divide by our unadjusted survivors to get our frequency after our selection. Our fitness also tells us what type of selection we should see, and in this problem, our frequency should be directional. Our frequency after selection value should prove that it favors big Bs in our population, and after an infinite number of generations, our population should be homozygous. And these are my references.